Hi, so this is 0 to 1, Exploring the Mystical Mathematics of Creative Coding, bold title. My name is Francis Stokes. I mostly do JavaScript stuff. I work for this company, We Are Reasonable People. It's based in Rotterdam. Web agency, we do really cool stuff. But in my free time, I'm making this YouTube channel called Low Level JavaScript, where I'm building like compilers and virtual machines in JavaScript, which is something that's questionable, but if that sounds interesting, talk to me afterwards. But that's not what I'm here to talk about today. No, today I'm here to talk about beauty and creativity and the pursuit of artistic endeavor. And I'm talking, of course, about mathematics. That might not be the word you associate with those three things, but throughout history, many people actually have. So Leonardo da Vinci, famously massively influenced by mathematics, was a mathematician, the other Renaissance artists too. And you actually, if you look around in religious architecture and such, you will find mathematics everywhere. And it's because it sort of like evokes this feeling of otherness and this beauty that's beyond human imagination. Now, obviously, I don't think you're going to leave today painting like Da Vinci or making this kind of stuff. But what I do want to leave you with is like some techniques and some methods of thinking that you can go out and apply in creative code. So what I'm going to do with the techniques is I'm going to break them down into like purely isolated examples, which might seem a little bit boring on their own, but when you start assembling them together and composing them, you can get some really interesting stuff. Before we dive into those techniques, I will show you some examples of the bigger things you can make. So I like to make stuff in JavaScript and HTML5 with the canvas. So this is the kind of stuff I like to do. It's all like procedural and purely functional in the pure sense, not in the functional sense. But actually, it doesn't matter what languages you're coming from. You can apply this stuff anyway. We're going to only look at math today and not at specific code. And as long as you can draw things like circles and lines and shapes, you'll be able to do this in anything. So hopefully you'll be armed with the knowledge and you can go out and do it in whatever you like. So the main idea that runs through my own development philosophy, but also lots of people's, is, you know, everything is really just about transforming one signal into another. And it's kind of a weird word, signal, that I've used there, but I've used it for a specific reason. You know, if you're from a electronics background, you probably think of signals as being like these voltages that change up and down. And if you're from a musical background, you probably think of signals as being like frequencies and this kind of stuff. If you're from certain models of event-driven programming, you'll think of signals as being like these events which pop up and you can handle. And there's a common thread under all of that, and that is like a signal is sort of a series of values over time. But since this is mathematics, let's be more abstract than that. Let's say it's a series of values over anything. Time is one dimensionality that we could look at, but in this particular description, I would like to think of even things like arrays as being signals, because you have a series of values, and the dimension is sort of like the dimensionality of the array itself. So that's what a signal is. Now, a more concrete example, because that's abstract, let's jump back concrete, would be something like time. And we're going to use this in every example. We're going to have a signal called time, and it's just going to count up from 0, and it's going to indicate 1, 2, 3, 4. It's the number of frames that have elapsed. So we'll have access to this in all of the examples that I show. And we'll have access to a couple more things, obviously. So we're going to be drawing stuff into a space. And that space has dimensionality, so it has a width and it has a height. Anything we put in that space has a position, x and y, so we know these things. And any objects, they also have dimensionality themselves. So squares have this one side length. Circles have radius. So we know these things. This is going to be our sort of character, if you will, throughout the examples. It's a square. and we're going to try and breathe life into this square with mathematics. And hopefully, by the end, you'll see how you can take something which is, a still square like this and turn it into more interesting things. So, starting simple. Let's say the square's x position is going to be equal to whatever the time signal is right now. Little t is the time signal. So this is what that looks like. Not terribly exciting, but it is going. And eventually, the square is going to make its way off the edge of the screen. And that's the last we see of it forever, because its x position is equal to time. So the width of the screen is limited. We need to fix that, because the action should be on the screen. We can use the Modulo Operator. Many of you will know that as the is a number even or odd operator, but actually it does a little bit more than that. So modulo is like division, but you get the remainder after the division. So 18 modulo 8, or we can divide 2 clean groups of 8, and then we have this 2 left over on the side. So that's what the modulo operator is. If we turn that back to our example, we take the time signal and we modulo with the width of the screen. What's going to happen is we're going to count all the way up to width, and eventually we're going to have the same number as width. And then we're going to divide cleanly. So we'll have 1, and then we'll reset back, because everything after that is just going to be now an unclean division, if you will. So that looks like this. The square makes its way off the side of the screen, but he pops back in afterwards. So also not interesting, but we'll get there. How about going faster? Faster's cool. More speed, more cool. So let's go 3 times faster. You can multiply a signal by a constant. We've chosen 3. So now we're 3 times faster. And that's, there's more life in that, maybe. We can go faster, but we can't say, for instance, I want this animation to last 200 frames. For that, we need to think about doing something else. So you might naively think, oh, well, let's use modulo again. Let's use modulo 200, and that way we'll get a 200-frame animation. And it's true, we will, except the square's going slow again, and he doesn't get to the end. So that's a problem, but it's easily fixed. We can do something called relative fixed animation length. I don't know if that's the actual name, but we're going to make a new signal called capital T, and we're going to say, we do this t modulus 200 thing, but then we divide by 200. And if you think about what that means, we're creating a fraction, and that fraction on the top half always has numbers that go from 0 to 200. And on the bottom half, we have 200. So we're always dividing by a fixed number, or another way of saying that is, t is always between 0 and 1, inclusive. So that is actually what the title of this talk comes from, this 0 to 1 range. The 0 to 1 range is a sort of magical place where you can perform certain kinds of mathematical operations, and they don't work like they do in other numerical ranges. So 0 to 1 is really cool. We're going to look at some of the ways that it's cool. One of the ways, it's kind of incidental, but now we have this t variable. It never goes outside 0 and 1, so we can just multiply it by the width. And then we get this. And that's a 200-frame animation where we've gone from one side of the screen to the other. So we've achieved the goal. We've turned it into a more speedy, fast square. But as everyone knows, linear animation is boring. Does anyone work with motion designers in their jobs? No? Oh, yeah, there's one. Motion designers hate linear animation. They say words like ease in and ease out. And really fundamentally, what they want is a curve, because curves are cool and dynamic, and they turn boring linear animation into something cooler. And we can get a curve like this by squaring the signal. So we're going to square the relative time that goes between 0 and 1 and multiply it by the width. And if you know anything about squaring numbers, then you probably know that when you square a number, they start to get really big, but not in the 0 to 1 range. Any number in the 0 to 1 range, when raised to a positive power, will stay in the 0 to 1 range. That's not a small thing. That's a really powerful and amazing concept. And kind of what happens there is that number, that sort of numerical range you've created, takes on the characteristics of the curve. So now we have something like this. So it looks a little bit choppy on this massive screen, but it looks smoother on the little one. We have acceleration now. So the square starts off kind of slow, and every frame is building up more and more speed, and by the end, it's like it's sprinting. So that's already way better. At the moment, we can't solve a problem like this. So we want to go from 0 to width in the x position. But if we wanted to go like 25% of the width of the screen until 75% of the width of the screen, so the square is only now in the sort of middle half, we can't do that with our current set of techniques. We need to get a new technique for the tool belt. And that technique is called linear interpolation. I don't expect anyone to like memorize this or like understand it or like right now. It's a reference. You can look it up later. What we have here, we can break it down a little bit. What we have is a place where we're coming from. That's our A and B. So we have a value x that we're plugging into some function, some linear interpolation function. And our x value is between A and B. So we supply those. And we're going somewhere. So in our case, we're going from the 0 to 1 range. We want to go to 25% of the width of the screen and 75% of the width of the screen. So this C and D, that's where we want to end up. And then this equation at the bottom, it's actually broken up into two parts as well. So the first part takes this x variable, and it normalizes it. And what that means is a fancy way of saying it puts it in the 0 to 1 range. It just so happens we're already in the 0 to 1 range, but if we weren't, this would do that step. The second half of the equation scales into the C and D range. Now, I think it's good to have a visual example of what this means, because this kind of on its own doesn't mean much. So imagine we have two lines. And what we've done is, even though they're different sort of sizes, we've kind of scaled them to be the same size. And the endpoints of our lines, like in this case 0 and 1, and then on the bottom 25% of the width of the screen, 75. What we can do is just take any point on our target line and just sort of drop down to where we are on the other line, and that is the interpolation. That's why it's called linear interpolation, because basically we're dealing with lines. Nicely enough, this works in many ways. It doesn't really matter where you're coming from, where you're going to. So it doesn't matter if you want to go from an ascending range into a descending range. You can do that all with this same function. So armed with that, now we can do something like this. We're coming from 0 and 1. We're going to 25% of the width of the screen, 75. And we just say x is equal to this m of t. And m here is just like mapping between the ranges. Math has bad names. That looks like this. So now we're going from that A range to that B range. Now, this is boring in and of itself, but I think it could be like, could be given some personality if we add just one more thing. And that is, if when the square comes in on the left, it starts out like completely transparent. And then as it gets towards the middle, it becomes less and less transparent. And then as it's fading out, it also fades out transparently. So it sort of seems to come in and out. As a curve, that would look like this. On the x-axis here, we have time. And on the y-axis, we have the opacity value of the square. This curve looks suspiciously like another curve from mathematics called the parabola. And the parabola is defined by the same equation we looked at earlier, which is just x squared. It's not super interesting. But if you look at it, what we've done is we've sort of pulled back the curtain into the negative side of the numerical spectrum. And you can see there's a beautiful sort of corresponding mirror image of the x squared curve. There are two problems. The first problem is that this curve is clearly upside down. We want this, but we have this. That's kind of easy to fix. We can flip it upside down just by altering the equation bit. We just say y is equal to 1 minus x squared instead. And that takes care of the flipping when your numbers are in this range. Now, The second problem is that we have, along the bottom here, we need our number to go from -1 to 1. But we have a number that goes from 0 to 1. And we need to do this somehow, but we've just learned a new technique, linear interpolation, so we can use that. So we use linear interpolation. And if we break this part down, this m of t part, what we're doing is we're mapping our t variable, our t signal that goes between 0 and 1, and we're turning it into a signal that goes between -1 and 1. And then we square it. That gives us the parabola, the nice curve. And then we say 1 minus this whole thing to flip it upside down. And then we have this opacity value, this O. And we can plug that directly into the square, and that will now look like this. And I don't know about you, but even as just like one isolated thing, I think that adds so much personality and dimensionality to this thing, which was previously just sort of popping in and out and didn't really look very cool. Now, there are more mathematical things that live in the -1 to 1 range. For instance, sine waves and cosine waves. Now, sine waves and cosine waves, they are like some of the coolest, most deep and interesting functions in mathematics. They extend into like every single area that you wouldn't even think they're connected with. They run very deeply, but they can be used as a tool just to try and create beautiful things because they have a predictable range. So when you have a sine function, anything you jam inside the sine function will always spit out a number between -1 and 1, as long as your input is valid, of course. So we know how to deal with predictable ranges. We have linear interpolation. So now what we can do is we can say our range goes from -1 to 1. It's the output of this sine wave here. And we just plugged little t in there, the original number of frames, because the sine function can take anything as input, so we can just plug that directly in. And then when we map that, we end up with this. So now the square is ping-ponging back and forward between two places. Again, isolated examples. So these are very much things on their own. Sine waves are really cool for something else. So as a mathematical object, you can have two sine waves, and they can be sort of oscillating at different frequencies. And then you can take those two sine waves, and you can add them together. And then what you get is another wave that has interesting characteristics of both of those waves, but in a way that's sort of greater than the sum of its parts in many ways. You can see here that this white wave is like jumping up and down and dipping back. If we were to use this as a signal to drive things in our animation, we would have a much more sort of seemingly unpredictable kind of input, but in a very mathematical way. So how does that look in terms of equations? Because everyone loves equations. So we have a wave like W1. We define that as being the sine function. We plug the time oscillator, the time in frames in, and we multiply it by some constant. And all that constant does is control how the frequency changes. So if we have two different coefficients there, two different multipliers, then we'll get two different frequency waves. But there'll be two waves. And then we just need to add them together. And if we want to get this back into the predictable output range, then we need to divide by the number of waves we have. You can add as many waves of different frequencies together as you like, and you just need to divide them by the number of waves you have. So taking that, imagine that we've made a bunch of complicated waves in this way by adding them together. I couldn't fit all that stuff on the screen, so I shortened it down a bit. Now we're going to modify different things about the square. So we're going to modify the x position, but we're also going to modify the y position, and we're going to modify the size of the square. And we're going to do that all by using linear interpolation on a bunch of different waves. And the result of that is something like this. Now, I've added a sort of ghosting effect to the background, so you can see how the waves draw out. But I don't know about you, but this feels like it has personality now. Like, when I look at this, I feel like the square is like a small puppy who's really excited that you've come home and runs towards you, but then can't handle it, so it runs away again, but then it realizes it's excited, and it comes back. And so we've just added some waves together, but it's given so much. And you can take this idea very, very far. Okay, I want to take a small side step. into polygons. Sounds really cool. Polygons, just like triangles, squares, pentagons, hexagons, septagons, blah, 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 blah. You just keep going. As you add more and more points to a polygon, it starts to look more and more like a circle. In many ways, you could think of a polygon as being an approximation of a circle, if not a very rough approximation. So that means that we can use the circle equations to generate polygons. And what I've done here is I've made a new function here called capital P, that stands for polygon, obviously, and it has two inputs. One of them is the number of points in the polygon. If this was a square, that would be 4. And I is the point we're interested in. So is it the first point, the second point, the third, or the fourth? And then what we do is we plug those into these circle equations. And you'll see here that the I divided by m part, that's us normalizing this number, putting it in the 0 to 1 range. And then we multiply it by 2 pi, which is like fancy math speak for 360 degrees. And what that gives us is the xy point of the object. Of each point that we're trying to get for our polygon, be it a square or something else. So that would give us something like this. And hopefully you can see how this sort of approximates a circle in some way. You're just like, you get the first point, and then you sort of divide by 4 the whole way around the circle, and then you end up at this point, and then you end up at this point. So it's a way that we can do that mathematically. So now we can plug that in, and we can say, I want the number of sides, or the number of points of this polygon to be defined by us mapping some sine wave into a number of sides. So what I want to get out here is either 3 sides or 7 sides, and all the numbers in between. So I want to go 3, 4, 5. And what I've done here with these brackets, that's just mathematical notation for rounding. I don't know why they chose that, but that's what it is. That's going to look like something like this. So you get this nice effect of a polygon sort of folding and unfolding itself. And we didn't have to do very much for that, but it works. But this is like thinking in the box a little bit, right? Because nothing about those circle equations says anything about integer numbers of sides. Like, who cares if we say we want a shape with 4 sides, or if we want a shape with 4.5 sides, right? What does that mean? Who knows? But the equations will let you do it. So what we can do is we can take out the rounding part, and now we're going to generate sides like 3, 3.1, 3.75, like all of these kind of weird numbers in between. And we're going to vary the radius of this polygon, because it's like a circle. It's a circle approximation, so it has a radius. We're going to do that based on a sine wave and just multiply it by some different frequency. It doesn't really matter. The radius is going to change. And then what we get is something like this. So now we're really smoothly folding and unfolding this polygon on itself. I think this is really cool. And also, what we've done with the radius part is we've chosen a frequency which is related to the frequency of the wave that controls the number of sides. So basically, they're divisible by each other in some nice way. And that means that they kind of line up together. And when things line up, they look pleasing to the eye. That's just how it works. And that's why all of those religious iconography things look so beautiful. It's because they're sort of, if you talk about them as being mathematical objects, they're kind of like multiples of each other very often. We're still thinking inside the box, right? Because like we're just drawing this thing to the screen. But it's a signal. It is itself a signal. So we've got a shape, and it's changing over time. What is a shape but just an array of points? And I've already said, right, that an array is just a signal of itself. So why don't we do something like this? This is the fanciest looking math I have in the whole slide. So what this says is that for every point P in the shape, we're going to generate a circle from that. We're going to generate a circle signal from that. And what we're going to do is we're going to give it the position P, so we give it the position of the polygon, and it has some fixed radius based on the height. And that looks like this. So cast your mind back to when this shape was folding and unfolding. this is now what controls the position of these circles. So we've gone from just like drawing a shape to like using a shape to generate the next most interesting thing we can do. And now you can really see the frequency thing happening, right? Because the way that the circles come back together and overlap in that specific way looks really cool. At least I think so. What I've done is I've made this like monstrosity animation. Like, it's not pretty, but it was just like to illustrate that you can do all of these crazy things. And using all the techniques I've shown you today, I've like modified all these different properties. So that like anything I could think of to animate, like the scale of the screen, the scale of the objects, like everything inside, I'm messing around with it using waves, using Modulo, using all these different things. It's not beautiful, but I hope it illustrates the point, right? Like if you look there, you see like there's these, now we're drawing different size shapes. They have different numbers of sides. Like inside each shape, there's like copies of itself where you have a gradient going from one to the other. The number of copies changes. Like you can modify all these things with these simple mathematical operations. And I promised that I wouldn't show any code. There I have one code slide. I don't want you to read it. It's not even important. But it's only around 40 lines of code to do this. And like this is like a way of thinking in this more like declarative way. Like you generate signals and then you use them on each other. You don't mutate anything. Everything you create is a new thing. So the reason I chose to use the word signal in the first place, rather than data or something else like that, is because a few months ago, I got really obsessed with making this project that I called the Modular Animation Synthesizer. Does anyone know what a modular synthesizer is? A couple of people. For the people that don't, a modular synthesizer is a machine that looks like this, and it's made up of modules, right? And it's an instrument in many ways. In many ways, it's not. So what you do is your modules, you have something that like maybe generates a wave, you have another module that changes the shape of that wave, maybe you have another module which like mixes waves together in weird ways. And every module has inputs and outputs. And the outputs and the inputs, they're all just audio signals, right? It's all audio. And when you plug in an output into an input, you're controlling something using audio. So if you think about it, what you could do is you could plug it into the speakers and you could hear what it sounds like, or you could plug it into another module and you could use that to control something. I hope you see the parallel here with like the shape that I've generated, which we drew to the screen, or we use it to generate something else. So the Modular Animation Synthesizer is a really ugly app I made. I did all of this with like the canvas, and the part on the right is React. But what this is you have a bunch of visual modules. So we have the time module that spits out a time in frames. We have mathematical modules that do mathematical operations. We have things for interpolation, both linear interpolation and nonlinear interpolation. Things for generating shapes, things for dealing with points, things for doing all these different operations, and obviously drawing. And it had things like multiple select and multi-move. And you can generate these really cool sort of mathematical, fractal, beautiful images from it. And many of these images, I wasn't able to think of them when I was writing code, because my mind is on the code and like the kind of all the different statements you have to write and keeping the variables in your mind. And when you have this sort of modular synthesizer style sort of visual programming model, you can abstract that away. You don't have to worry about it. And you can just think, oh, what if I plug this thing in this thing? What would that do? What if I controlled this based on that? And that's harder to do with code. It's not impossible, but it's much easier to think about things like this. So I have this on my GitHub. You can check it out. It's not very super polished, but you can certainly play with it. That's where I want to end today. So this QR code will take you to my GitHub. You can check out some of the projects there. I'm Francis R. Stokes, if you can't find it that way. Check out low-level JavaScript if you're interested in some weird compilers in JavaScript. And thanks very much. It's possible. Yeah.
Thank you, Francis. That was great. Does anybody have any questions for him before we move on? No? Oh, one question. I'm going to go over there and I'll come to you.
Well, I really like the visual math part, but at high school I hated maths. So I want to try it again, and maybe there are some nice resources or things like that. Yeah. Where can I catch up or something?
Yeah, I hear that a lot, and I also really hated math at school. Nice. I think it's just the way they teach it. It's just they do it in this really boring way. There are indeed some resources. So for doing the drawing stuff, you can look at something like P5.js. It's a really, really nice, it has loads of stuff built in, it has a lot of this math stuff built in that you can just play with it straight away. But yeah, I think the main thing to do is just like start experimenting. Just like play with a few of these things, play with sine waves, they're really cool. You can do tons of stuff with sine waves. Play around with those for a while. Just see what you come up with, and you'll naturally bump into questions. And I think if you start Googling things like creative coding, how do I blah, 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 and you'll find things. There's a lot of stuff out there.
All right, perfect. Thank you.
Cool. Oh, and actually, I'll make this presentation available, and I'll put some links also in the GitHub description. So it's not there now, but if you check back in like a day, I'll put it up.
Hi, yes.
Hi.
Well, your implementation looks amazing.
Oh, thanks.
Yes, I have one question related to that. Is it possible to connect the MIDI devices to one particular parameter?
Yeah, actually it is. I've also built in audio as an input. So if you play around with this, it will first pop up saying, do you give access to your speakers and stuff? That's not because I'm trying to track you and listen to you in your house. That's because there's a module where you can take audio in, and you can put out signals related to the audio. So that might be the frequencies, but it could also be like analysis on the audio, like the kind of doing like a Fourier transform and getting some more different outputs from it. So you can control everything based on anything, actually. And if you wrote other modules that were based on, if you connect a piece of hardware and then get a signal from that, you could map it in this way too.
I was wondering, what do you do with the outputs that you get? Do you can you export it? Do you export it to a movie, or do you put it in some kind of vectorized movie? Or
this project is really like a Frankenstein project. So what happens is you create this big JSON object that describes all the connections and everything, and then basically, I have a sort of compiler which runs through that JSON object and works out all the dependencies and if they're met and all of that kind of stuff. And then it generates JavaScript code for that. So what it does is, because if you try to calculate that every frame, you can't draw the animation. It's super slow. So what I'm doing is I generate the code that makes the animation based on the graph. So it's a little bit of a weird machine, but what you get out is code in the end. So you could do anything with it. You could either film it and get it into a video or a GIF, or export the frames. Or
can you directly pop it into a website?
I didn't finish this feature. I would really like to. Technically, you can. Yeah. So if you can run, it has a runtime, so something that describes how to draw a circle and a line and stuff. If you have the runtime alongside your animation code, you can run it in a website.
Cool.
Thank you. Can we get another round of applause for Francis, please?